Welcome to my talk about a new constant expression interpreter for Clang. My name is Tim. I work at Red Hat, as you can see. And if you're in the audience today with a slight déjà vu feeling, that might be because of this talk. That was in 2019, 5 years ago. And it's pretty much the same title. And now I've ripped off not only the title, but also the second slide from someone else. So that's a good start. And this is Nando Licker. He did the initial work on this. And I don't know how far he actually got. But in 2019, there was one commit push to the actual repo. I think the commit message was something about the skeleton of the new interpreter. And that was it. I picked this up in 2021, so I'm going to compress 3 years of work into the next 20 minutes. Should that be running? Okay. Yeah, this is about interpreting expressions at compile time. The difference to the current interpreter is that for const_expr and const_eval functions, we don't look at the AST every single time we call them, and instead we compile them to bytecode once, and later only interpret bytecode. This is supposed to be faster. For expressions, we still interpret them directly. We don't emit any bytecode. You can see that later. For the basics, everything about the interpreter is in the Clang interp namespace. We have yet another class called context, and that keeps a program around. A program is just a list of global variables, basically, and all the functions we have compiled, and of course the bytecode. And we have the usual reference to an AST context. In Clang's expr class, there's a bunch of API for evaluating an expression. You know, they have evaluate as known constant, evaluate for overflow as Boolean condition, and so on. But in the end, they all call one of these four. The first one is potential constant expression. And I'm not exactly a big fan of the name, but it takes a function decal, and this is essentially what compiles the function to bytecode. Evaluate and evaluate as R value, take an expression and evaluate it, and hand you the result. The as R value variant performs an implicit L value to R value conversion at the end. And the last one is evaluate as initializer, which, you know, takes a var decal, evaluates the initializer, and hands you the result. So with that knowledge, as a warm-up, can anyone tell me how many things are being constant evaluated when I run this code using that command line? Does anyone have an intuitive guess who doesn't know a lot about Clang internals? You can just yell it out.
0.
0 is wrong, okay. But it's a valid guess. Does anyone know more about Clang and can give me a different guess? It's higher. Sorry, what? Can you express that in a number?
7, 8?
8?
7. Let's go with 7. Yeah.
Okay, 7. It's also wrong, but of course I'm asking that because you can't get it. I would probably have to ask like 16 people before I get the right answer because it's 16. You know, we evaluate almost all of these for overflow, including all the literals, and then you of course need to know that this is a C++ range for loop. So there's a bunch of implicit variables you don't see. And yeah, I just want to say stuff is everywhere, and we probably do it more than you think. Yeah, I already mentioned the program. The function is basically what you expect it to be. It's the compiled bytecode and a bunch of more information about the function. Yeah, we have a class called compiler. So your compiler now has a compiler, and that is what compiles functions to bytecode. Depending on the emitter, of course. If we have a bytecode emitter that actually generates bytecode and an eval emitter that instead of doing that, immediately evaluates the instructions we emit. The bytecode is stack-based, and this is what we use the interp stack for. And the interop frame is essentially your usual function frame, local variables, has a size, and so on. For types, we also, this is really, it's probably not interesting if you already know programming, but there's a bunch of, integers of different sizes. There's floats, we have pointers, and so on. We don't have anything for vectors and complex types specifically. We just use, an array of primitives of the right size, which for complex types is simply 2. And for classes and structs, we actually generate records. And that is simply information about the class or struct. And especially, we compute offsets for bases, fields, and virtual bases. And then later, when we refer to a field, we just do that by using that offset. For pointers, the most important one is the block pointer, which is not the one you maybe know from Objective-C, but it's just, a block for us is like actually allocated data. So if you have an integer somewhere, we need to allocate it. Usually that is in either the interop frame for local variables or in the program for global variables. More recently, there's dynamic memory allocation that also works at compile time, which is, it also allocates a block. To describe the contents of a block, we have what we call a descriptor. And a descriptor, gives us like all the information we may possibly need about the data inside a block. If it's an array, it gives us the size of the array, the element type. If it's a record, it gives us the record, and so on. And for fields, they are always preceded by what we call an inline descriptor. And the inline descriptor then gives us data about the field, like the descriptor for the field. Or most importantly, there's a bit whether the field has been initialized at all. So as an example, I brought a struct. And for this struct, we're going to compute the offsets. And the offset for field x is going to be 16, which is simply size of inline descriptor, right? So if you want to refer to the field x, you would point to offset 16 and then forward from that offset is the actual data of the field. The same is true for y, of course. The 4 bytes of the actual integer are then followed by 4 bytes of padding. And for the float field, we simply, we end up at offset 64, remember that. And the size is, in this case, 32, which is size of AP float. Like for floats, we also use AP float. And in green here, you see yet another bit of metadata we need for global variables. In this case, it's just the initialization state. Global variables have to be initialized if they are declared const expr, but that may fail. And if it fails and we then later use the variable, we need to properly diagnose that, and this is what we use that for. And if you now refer to the y field of a player variable, you would point right after the second inline descriptor, which is right before the actual data of y. Okay. I would like to actually look at interpreting a function, right? And I just added a member function to the player struct, and I declared a global const expr variable called p, initialized it, and the expression I want to look at is the binary operator in the static assert. That's an equality, right? And the left-hand side is a member call, and the base of the member call is just a decorative expression, which is just p. So when we evaluate such a decorative, it's basically going to end up as a pointer on the stack, right? And at this point, we start actually evaluating the getHealth function. So down there is this all stack, right? So we start with a pointer, and the actual thing is not really interesting, but it's a root pointer because we haven't yet applied any offset to it. And so if you remember the body of the getHealth function, it was just return health, but of course that's an implicit this arrow in front of that. So what we first do is we get our instance pointer. And the instance pointer in this case was p, and so what we get is simply the exact same thing. So we have the pointer twice now. What we want to do next is get the health field on the stack, right? So we do that using the getPutterFieldPop instruction. maybe you can figure out a pattern for the naming yourself, But the get put or field pop instruction will pop the top of the stack, apply an offset, and then push the result back on the stack. And this is where we have the offset 64 that we saw before. And so the result is just gonna, points to the same memory, but has the offset of 64 applied. And next, we want to actually load the value, which is not surprisingly gonna be our 30 from before. And just like in every other function invocation, we return using a or we end it in a return instruction. And that will pop the return value from the stack, clean up behind the function call, meaning remove all the arguments passed to the function from the stack, destroy the interp frame, and then just put the return value back on the stack. And this is then where the caller of the function may actually use it, right? So the binary operator now has the left-hand side evaluated, and of course now it's going to evaluate the right-hand side and compare those. It's going to be equal, as you can see. And so the result we will then evaluate to, or convert to an AP value. This is the only time in this case that we will convert anything to an AP value. And we will return that to evaluate as R value. And your compiler is not going to yell at you because the assertion did not fail. Yeah, I brought a bunch of performance measurements, and I don't think the two interpreters are in a state where you can meaningfully, compare the performance. But given the topic I'm talking about, I felt like I have to. Yeah, this one has a GitHub issue number 61425. So definitely there's a real need for this, and so you can now do nothing but faster. This runs in like 4 seconds instead of 11. If you want to compile Fibonacci numbers in a really, really inefficient way, you can do that now, and it's faster. Here, see, I used embed, very modern, and the file I'm embedding is the SQLite3 amalgamation. That is around 8.6 megabytes, and I'm just summing them up. I'm touching every byte once, and yeah, it's also like 18 versus 31. Yeah, so far so good, right? I mean, I have the SQLite3 file anyway, so I can just run it, and that proves that I'm not making the numbers up because now it's slower. I'm not sure why yet. I haven't investigated, but again, I'm just like you can compare these, and I'm still trying to make things work. I haven't actually invested any or a lot of time into improving performance. For testing, we have the usual directory in the Clang test directory, and we're also adding more and more new run lines to existing files. By the way, if you want to try this, this is what you need to pass to Clang. And in April this year, I started periodically testing the entire Clang test suite. I was at almost 600 test failures when I started, and I am now at, well, in this graph, it's like 179. If you go to the website link below, it's 175, and if you look at my laptop, it's 156. Yeah, so general trend is downwards. I did one boo-boo up here, but I'm working on it. Yeah. Oh, okay. I'm not gonna. Yeah, I need to fix built-in constant P. I'm not gonna tell you what it is because I don't want to ruin anyone's day or life. But it is this weird combination of things we need to do at when generating the bytecode and then later when interpreting it. It's also, as far as I know, a GNU thing. And if you look at how Clang, or what Clang does when you use it, it's completely different than what GCC does. Yeah. Type ID pointers aren't really, I have nothing interesting to say about that. It's just a bunch of tests that would be fixed if that was implemented. Built-in bitcast is just a lot of work. Is Aaron here? Yes. There's a patch waiting for you. It's like the most pressure in one ping I can use. Yeah, so, but it's better than the current one because it supports bit field, right? And array fillers is, you know, when you declare a huge array and then you only initialize one element of it, then, you know, it would be nice if we didn't create a huge array for you. And I think I'm done, and I would now take questions. Yeah.
Hey, thanks for the talk. I was wondering, how do you test to make sure you've got the semantics right when you're doing the constant evaluation, say, versus, oh, you removed all the context, but then you compiled it natively and ran it. Like, how do you make sure you got the semantics right?
Well, you can write your tests in such a way that they are definitely run at compile time. Like if you make sure that you can make sure that an initializer is evaluated at compile time by making the variable const expr.
Sorry, I don't quite follow, but I can ask offline.
Okay.
I just wanted to say thank you, because the new constant expression interpreter, I think, really is the future of Clang. It is significantly faster, despite putting in no real effort on optimizing it. And it's a huge undertaking. So thank you for working on it.
You're welcome.
Hi, I'm going to try to repeat the question from the previous one. So how do you make sure that when you do constant evaluation, the results are the same as if you would run it without constant evaluation when you do the whole compilation?
I don't really do that.
You just hope it's the same. You're like,
what I'm trying to do is do a drop-in replacement for the current interpreter. So whatever that does, I try to do.
So you just run all the tests and hope they just have good coverage?
Basically, yes.
It makes sense. Thank you.
Does anyone have any other questions? We have time.
Have you thought at all about moving away from AP value as the representation of the final result?
I mean, yeah, kind of. But, you know, it's used a lot inside Clang. So I think that's something we can do after we switched interpreters. There's a bunch of other things we could simplify.
Sure.
But, yeah.
That makes sense.
Well, let's thank Tim for his talk, and we'll take a 5-minute break.